Hi, welcome to Unit 47. In this unit, we're going to talk about satellites and rings. Those are objects that revolve around planets. And especially in this case, we're going to focus mainly on the outer planets because they are the ones who have satellites. You're saying, well, how about the Earth? It has a satellite, which is the moon. That's the exception, actually. It's not really the rule. So the focus is going to be on the outer planets. So describe the overall properties of satellite systems and define their shapes, basically. Most of the times, if a satellite, I mean a moon in this case for the most part, or a ring system, if it's orbiting in the same direction with more of a spherical shape or close, not spherical, circular path or close from a circular path, then this is a regular shape. Anything other than that, it's not regular. So that's really something that we have to talk about. And then compare satellite systems and their formation processes to the solar system. Explain the difference between large and smaller satellites. You will notice the biggest difference is their form. The big satellites, the big moons, are spherical in shape, and the smaller moons or the smaller satellites, they're irregular. They're potato-like shapes, basically, any shape that you can think of. Okay, and then we're going to describe the ring systems and where they come from. Okay, because if you look at Saturn, for example, you see a huge ring system around it. And the question is, how come other planets do not have it? As a matter of fact, hold on that thought for a second, okay? The other three big planets do also have rings. I mean, they are not as obvious as that of Saturn, but they do. But like the case of the Earth, it does not have a ring, for example, going around it, a ring system, that is. So the first moons were discovered by Galileo, other than, of course, our own moon. Uh, when he looked at Jupiter, he saw this four moons going around Jupiter. Hence the name. They call it the Galilean satellites because he's the one who discovered them. These are in the 1600s. Uh, the moons are small, of course, and their period, basically the time it takes for them to go once around Jupiter, anywhere from around 2 days, it's actually slightly than 2 days for the case of Io, all the way to 17 days for the case of Callisto. So those are the moons of Jupiter. Okay. So from there, we know that other planets also have moons. As a matter of fact, they have a lot of moons. Okay, a lot of satellites. So here they are. In this picture, let me go into the next one because it zooms on this picture is better. So here they are. Okay. So what I have in here is the distance from the center of the planet. The case of the Earth Moon, it's about 300,000 kilometers, okay? 384,000 kilometers to be more specific, okay? So the range is between 10 to the power 5 is 100,000 and 10 to the power 6 is a million. So that you know, this is a logarithmic scale. This is not linear scale. A lot of times when we do astronomy, we do a logarithmic scale because it compresses the scale into a region that we can see. Because if you're telling me this is 100,000, then the next grade will be 200,000, 300,000, 400,000. By the time you reach a million, it's out of scope, so we can't see it. That's why we use a logarithmic scale to break down so that we can see everything at once. Okay. Oops. So the Earth Moon is here. Relatively speaking, Io, which is the closest big moon to Jupiter, is almost the same distance from the center of its host planet, which is Jupiter, than the Earth's moon is. Okay? So slightly further, but they are the same order of magnitude. As a matter of fact, even in size, they are similar. Io is slightly bigger than the Earth's moon, though. Okay? What you see in this picture in here are color coded. First of all, the yellow color. These are regular moons. These are moons that go in, first of all, two things. They go on the same plane as the planet. So basically, they move on the same plane together. Okay, number one. Number two, their paths are almost circular. Okay. And number three, they are actually also tidally locked, meaning they face their host planet with the same, like the Earth moon. We see only one face to it, okay? So all of these things are indication that probably this was formed from the same stuff and the same time when the planet has formed, okay? In addition to that, I have another color coded. The biggest one of them is Triton, the moon of Neptune, but I have more of that. And you see them that they line up usually on the far side from the planet than the planet itself. And I have more of them for Uranus. I have also a lot of them for Saturn. And I have one and then more of them beyond this yellow region for the case of Jupiter. Okay, these ones are irregular moons, meaning their orbit not necessarily on the same plane. So they could be orbiting on this plane or that plane, whatever it is. It's not on the equatorial region of that planet. Okay, that's number one. Or, and in the same time, they could be in irregular shape. They could have a path that is more, basically, it has a high eccentricity, an ellipse, very high eccentricity in this case, okay? And they're not necessarily also tidally locked. And there is another point. They rotate in the same direction as the planet. Remember, we mentioned a few units before about the angular momentum. Basically, if you have a bathtub that is full of water and then you remove the plug, you will notice that the water will spin in the same direction going down, okay, until it sinks in. It's not like one layer of the water will spin in one direction and the other layer of the water spins in the opposite direction. It all spins in the same direction. And that has to do with something called the angular momentum. The angular momentum in this case is conserved. So when the stuff that was making up that planet and the same moons basically came together to form that planet and also the other chunks of the moons, it's the same stuff. So it was spinning in the same direction. So it retained that rotation in the same direction. Whereas if it's a captured moon, like the case, for example, for Triton, it did not form in the same region. So it could be spinning in the opposite direction than everybody else. Everybody's just going like counterclockwise. That moon probably is going clockwise. So those are what makes them irregular. So their direction of rotation, the fact that they are not on the same plane, the fact that they are spinning on elliptical paths, and that makes them irregular moons. So what is probably the hypothesis for all of these things? They must be captured objects. For the case of this tiny object, they probably could be most likely asteroids or probably even comets that gets ventured too close and they were captured. But for the case of Triton, it's probably a twin to Pluto, because remember, we are very close from Pluto at this point, we're near Neptune. A twin to Pluto, actually slightly bigger than Pluto itself, that somehow ventured too close from Neptune and got captured. Okay? Pluto also, from time to time, it gets actually within the orbit of Neptune. So again, so it must have been probably a dwarf planet that somehow got captured by Neptune. Okay, so that's probably the explanation for this moons. In addition to that, there is another color in here that you see in this presentation. The blue line in here for the case of Jupiter, for the case of Saturn, for the case of Uranus, and for the case of Neptune. It's exaggerated in Saturn in here because that's the ring system. It's continuous stream of particles in that case. So all of these planets do have rings. They're too faint and too dark for the other planets, with the exception of Saturn. That was obvious. It has a big ring system. So this is the moons. In terms of size, Ganymede is the biggest moon in the solar system by far, and it's actually bigger than Mercury itself, planet Mercury. The second in size, it's Titan. Titan is actually also bigger than Mercury. It's a huge moon. Okay, that's the moon of Saturn. If you have had a chance to look at the Titan with a telescope, you will see a big dot next to it. That's Titan. Okay. The third moon in terms of size is Callisto. That's the furthest moon from the biggest moons, that is, for Jupiter. Okay, it's about the size of Mercury. The fourth moon in the solar system in terms of size is actually Io. Io is the closest big moon to Jupiter. Okay? The fourth moon is the Earth. I mean, the fifth moon in terms of size is the Earth's moon, and that's slightly bigger than Europa. Europa is actually the next big moon, and then you have Triton in here, the moon of Neptune. So this is a good idea to try to know them. It doesn't make the other moons less interesting. As a matter of fact, there is more interest right now in Rhea, Iapetus, Dione, Tethys, Mimas, Oberon, Imbriel, Miranda. All of these moons are actually interesting. Universe, they have not universe, worlds basically of their own, because they have all kinds of, some of them have atmospheres, some of them have water, basically geysers coming from them, different structures on them, and there is a potential of life on them. So these interesting moons are the big ones that are interesting, but doesn't mean that the others are also negligible. So the others are interesting worlds of their own too. Okay. So in terms of size, these are the big satellites as I was talking about. Okay. The Earth moon is not listed because the focus again is not. The Earth moon is an exception because all of the inner planets really do not have moons. The Earth has a moon, and that's an odd thing, like we said in the unit on the moon. But the outer planets usually have moons, okay? Ganymede, Titan, Callisto, Io. Io is actually an interesting word by itself, and probably there is a unit down the road on it, on its surface, because it's a highly volcanic surface because of its proximity from Jupiter. So it's being basically tidally worked between Jupiter and the other moons, to the point that it has a lot of volcanic activities and you have a lot of sulfur in its surface. And then you have the smaller moons for Uranus, and there is a big one for Neptune, namely Triton. Okay, any moon or object that is 400 kilometers in diameter or more must be spherical in shape, because gravity would work it to pull it from every single direction to make it into a sphere. An object that is less than, or a moon that is less than, or a satellite that is less than 400 kilometers, there is not enough gravity to pull it from every single direction. It could have any irregular shape that it can have. Okay, so that's basically the biggest difference in them. These are the medium-sized moons, as I was mentioning earlier: Rhea, Iapetus, Dione, Tethys, Oberon, Titania, and Imbriel, Ariel. All of this are Miranda. Actually, it's a very interesting word by itself, and the size in here is really not that matter. Okay, and then in addition to that, you have smaller objects in here. The scale in here, this whole thing is 1,000 kilometers. So when you put it, probably Rhea and Titania will fit under that scale. Okay, and Iapetus too, probably. So some specific moons in here, like for example, Iapetus has these features that is on one side it's white, on the other side it's very dark. Okay, so it's also tidally locked to its host planet, namely Saturn, and its structure is dark, probably from the soot and the deposit and the volcanic activity that it has in the past, or some other deposits. Okay, if you look at Enceladus, it has so many geysers, so many basically ejecta in its surface, out of its surface, indicating that its internal structure is probably also liquid, and it's also because of the tidal forces probably keeping that or making that water erupt, some sort of a high geysers. Okay. In terms of Miranda, it has this high cliffs of 20 kilometers, indicating that it has some violent past, probably some sort of a either internal structure that causes some sort of a plates rubbing against one another, or some sort of collisions to cause this grooves and these cliffs. 20 kilometers, to put it in perspective, is a huge distance. You're talking about 12 miles. Okay. The Grand Canyon is not 12 miles deep, is not 10 miles deep, is not even 5 miles deep. Okay? It's not even less than that. Okay. So imagine that you're standing on a cliff that is 12 miles down. If you were to drop a rock, you're not gonna hear it hit the ground. Okay. So it's a very, very, you're not going to even see it go down. Okay, that's a very deep distance in here. So these are the cliffs on the Miranda. In terms of ring systems, obviously the first rings were observed for the case of Saturn because they are obvious. And Galileo, when he saw them, he didn't know what to make for them. So when he drew the picture, he drew them like ears, okay, like rabbit ears, okay. And it was Huygens later on that basically noted that they are not attached to the planet; they are actually separate from the planet. It's actually Maxwell who made an argument based on Kepler's laws that they must be tiny rocks, they must be smaller objects. Each and every one of them is following Kepler's laws, and that's basically what we know today. Okay, it's made up of three main rings. The outer ring, which is A, then the ring B, and the inner one, which is C. And in between these rings, there are gaps, okay? The biggest gap that we see is the Cassini division, and that's between rings A and B. Okay? If you look up close, actually, you will see that there are actually far more divisions than this. There are more gaps in between them, okay? And to the point that you have ringlets in here. So the leading hypothesis or the theory is, or actually you can observe it too, is that you have some tiny moons in here, and these moons are causing basically some sort of a circular waves, and those circular waves are the ones that you're looking at in your disturbances in this case, okay? As I said before, Saturn is not the only one that has rings. Too faint, but they are there for Jupiter. Uranus was observed during the passage of Uranus in front of another star, so we saw that the star dim in and out, and sure enough, when the first flyby basically pictured them, so we know it has rings, and so is Neptune too. All of them have rings, and their ring systems are, granted, they're a little bit less, but they're actually in there in terms of their structures, okay? Every ring system, they have this so-called shepherd moons, and they are probably the ones, I mentioned the fact that probably those gaps are also coming from resonance between the moons and the planet itself, and that resonance can create some gaps in between the structures, okay? So you have moons basically in between in here that can cause this moons basically to pull in each side and then cause these ring formations in there. That's why they're called shepherd moons, okay? How did the ring system form? If it were up to gravity and gravity alone, you bring an object that is held by gravity up to a certain distance, which is about 2.5 times the radius of the planet, okay, called the Roche limit. If you bring it there, the inner part of the moon or the satellite is pulled more so than the outer part because of the force of gravity. Remember, the force of gravity is inversely proportional to the distance. So imagine with me you have a planet like Jupiter. It's a huge planet pulling on every single object. And you put a moon next to it. That moon has a finite size. It's kind of has a radius. It has diameter. If it's far away enough from Jupiter, then in this case, that diameter doesn't matter, because if you are on this side of the moon or that side of the moon, the planet is very far away to cause a big discrepancy between this side and that side in terms of pull. But if Jupiter is close by, this distance is smaller than this distance. This side is being pulled more so than this side. That creates kind of an elongation, and the moon starts to tear apart if it is held by gravity. Because you're wondering for a second right now, wait a minute. If what you're saying is true, I'm standing in here, or I'm sitting, it doesn't matter. The lower part, my legs are closer to the earth than my head. Why am I not being pulled apart? Why my head is not, because my head is not being pulled as fast, as strong as that of my feet, for example. Well, in this case, remember, I said what holds the object is gravity. You're being held by electrostatic forces. So if there are other forces involved in this case, then then the object will keep its shape. That's why you have moons within the rings. They're still existing in there, so they are not torn apart because they're held by other forces. Let me explain this point here because it's very, very important to understand what's going on. If the object is too big, like Io, for example, if the object is too big, yes, there is electrostatic forces between this portion and this portion and this portion and this portion all the way to the end, but between the lower part of that moon and the higher part of that moon, the further part of that moon, only gravity is the one that causes it to be circular. So in this case, gravity will dominate. Okay? So adding another rock to that moon, what brings it in is not the electrostatic forces. It's actually gravity that's going to hold it. So an object that is big is really held by gravity more so than anything else on the global scale. And that's how gravity acts on the larger scale. On the smaller sizes, like if you take a small rock, for example, or me or you, even in this case, they talk about the satellites, for example. Well, they're too small. A bus, even a mountain, okay, it's too small to be held by gravity. It can retain its irregular shape, if you wish, because gravity is not strong enough to take the entire Himalayas and make it into a spherical shape. Okay, so the Himalayas, if you put it orbiting the Earth, it's going to stay intact. But if you take a moon the size of bigger object, much let's say spherical, 400 kilometers or more, gravity is the dominant force in this case, and gravity will give in if you bring the object within that limit of about 2.5 distance, the radius of that planet. That's how rings form. Okay, that's how rings form on the outer planets. Okay, thank you.